Okay, now we're moving on to pressure. We've talked about the sun's energy coming in and the influence on temperature. Well, temperature has a direct influence on pressure, and pressure has a direct influence on winds and other parts of the atmosphere. So we're working this game of everything is interrelated. So we're trying to learn the different pieces of the puzzle to start with here. And we've talked about temperature, now we're going to talk about pressure. Air pressure is really important and it's significant to understand how variations in it impact our weather. So with that, what is air pressure? All right, there's molecules all around you. You're made up of molecules. The air is made up of molecules. These molecules exert some kind of force on your body. Force is just mass times acceleration. Well, mass is just like a weight, except it's not quite the same. It's more, how many molecules can you fit in a small area and what is their mass in that area? So when we look at air pressure, we're thinking about, okay, how many molecules are there above this point on my head, for example? And how many of them are trying to move down on top of me? What's their acceleration? We know that gravity has an acceleration. We know that air can have an acceleration. And if you heat air, the air molecules are going to move faster. We've already learned that from temperature. So that will apply somewhat of an acceleration. So all of these are forces that add up in making what the air pressure actually is. And Dalton's law simply states that each gas in the atmosphere's pressure adds up to the total of what the actual atmosphere is. So in other words, if I add in water vapor, if I add in carbon dioxide or carbon monoxide or nitrogen or oxygen, all of that adds up to what the pressure is that we record. So air pressure depends on the mass of molecules and the kinetic energy of those molecules. So basically the weight is force of gravity exerted on a mass. So average sea level pressure, 14.7 pounds per square inch. Think about that. Every square inch of your body is weighed down by 14.7 pounds. So, however, your body exerts an equal opposite force of air pressure outward from it. And so do buildings and all. That's why they don't collapse. And how do we measure air pressure? We used to use a mercury barometer. Then somewhere along the line, somebody discovered mercury was bad for us. So we no longer use mercury barometers. Mercury, all it is, it's very heavy. So when you put it in a tube that had no air in it, put it in a pool of mercury, the air would pushing down, we can really see the weight of the air on the pool of mercury at the bottom, would push mercury up in the vacuum tube to some point. That would be the weight of the air. Now we have aneroid barometers and others to measure the same way. There are different things that make that. And we use different units of measure for mercury. I love to talk in millibars, partly because it makes life easier in the equations. But it's also what all weather maps are drawn in. Whereas we can use inches of mercury, pascals are very equivalent to a millibar. So now we go to air pressure itself in the atmosphere. So interestingly, guess what? Air is compressible. We just added another complication. If I had water, water is not compressible. You can't push it if you put it in a bottle and try to squeeze it smaller and smaller in there. You just can't do it. It's going to burst out. However, air you can. So since air is compressible, there is going to be a change in pressure the further up in the atmosphere you go. It's going to drop. And based on all of this, if we averaged over a bunch of seasons over a bunch of years, we can get a standard atmosphere where we estimate the pressure should be at this point, at this height, and should have this temperature. Now, horizontal changes in air pressure, they don't change very fast. Notice here, this is millibars, 1022 millibars, then something like that. Here we're at, 1,007 maybe. So 1022, 1,007, 15 millibar pressure change over time, over 24-hour period. So, and this is a typical low pressure moving by. So what are some of the influences on air pressure? Well, obviously, rising air temperatures increase the average kinetic level. And because Earth is not a closed container, the atmosphere is not closed, it fluctuates at the top. So there's not a top. That means that this density will actually, increasing air temperature decreases the density. So the molecules move further and further apart. So unlike if you had a closed container like you would have with a liquid and heated that liquid, and that would just be pushing more and more out pressure on the sides of the container, air doesn't work that way. Now, cold air pressure is going to drop much quicker in the vertical. Why is that? Well, cold air is kind of dense. So if it's so dense, then the faster we go up in the atmosphere, the faster the air pressure is going to drop. Now, if you go to the other side of that coin, you're very, very hot, the air pressure is going to drop slower as you go up. So we're going to take a look at that some today. Think about it. If I have a constant 500 millibar surface, pressure on that surface is all 500 millibars, nothing else. The area that has cold air under it, the pressure is going to be dropping faster, so that 500 millibar surface is going to sink. It's going to be closer to the ground. Oh yeah, where the air is hot, that 500 millibar surface is going to be higher up. So you can see all of a sudden we have different heights for this 500 millibar surface. And yes, humidity plays a role. Muggy air, believe it or not, is lighter than dry air. What? You're going to tell me? Because I always felt like it was so humid and hot. Everything seemed to be heavy. It's actually not. The more moist air is, the less dense the air is. So it's actually lighter. All right. We've said that the Earth's atmosphere is a fluid. So if I push something at the top of a fluid, it's going to have an impact on the bottom of that column of fluid. So this is where we're talking about converging air or diverging air. If I have converging winds that are coming together, they're pulling molecules all into that same area, right? So what they're doing is going to be pushing the air down or up, depending on whether it's near the Earth or up in the atmosphere. And that's going to impact that whole column of air and change its pressures. The ideal gas law, very straightforward. The atmosphere has expansional cooling. So we know that the pressure drops with height. So an air parcel can be any size you want it. Use your imagination. Just lift a parcel of air. It could be in a paper bag or whatever. As that air parcel goes up, it's going to try to expand, cover more area. That expansion is cooling. We feel it when we let air out of a tire. I know I've found it fascinating sometimes when I see air, when I'm pushing air in my tire or letting air out of my tire on my car. You let air out, it cools off. It's cold. That air is really cold. However, I push air in, it gets kind of hot. The same thing happens with an air parcel as it's being pushed back down towards the ground. It's being compressed, so it's warming. And here you can see the mechanisms at work. We know we can mathematically calculate how fast temperature would drop in the atmosphere if you just had everything standard. And it's a dry air parcel. So we know that it's going to expand, that air parcel, and therefore the temperature is going to drop. If it's dry, it will drop 9.8 degrees Celsius per 1,000 meters. That's why when you go up and down a mountain, you feel the change in temperature. It gets cooler the higher up you go, warmer when you're coming down. But moisture always messes this process up. We're going to talk about moisture in a couple of weeks here. And it is going to change the way that air temperature drops. What it does, it releases heat into the atmosphere when you have a cloud. When it does that, the air temperature doesn't drop as fast. That's changing everything. So with that, let's just take a peek at a couple things here. Here is current temperatures and pressures. What I see here is we got lower pressure up to the north here. Right there's the lowest pressure. I have low pressure there and cold. Look at this, 46, 45 degrees. So it's cold, low pressure up here. How does that reflect it in the 500 millibar surface? Well, we said pressure would drop faster the colder the atmosphere is. Through all layers, guess what? Pressures are low. Contours are lower for 500 there. Oh yeah, where it's hotter, they're higher. Further south you go. So these air temperatures impact what the pressure is going to look like. And with that, I wanted to just show you, think about the pressure change here for a second. If I went to 850 millibars, about 1,500 meters up, maybe a mile, and the pressure has dropped 150 millibars in that mile. Do you see anywhere on this map that kind of a pressure change is occurring? Look at this. We have 1,008 millibar low here. Way down here, almost into the United States, is 1,012 millibars. A little bit quicker pressure gradient up to here, but nowhere does the pressure drop like that. Now, yes, out here in the Atlantic, we have a hurricane. Pressure is fairly low down here. But even there, the pressure doesn't drop to that kind of an extent. So I wanted to just give you an idea if this comes up, and it probably won't because it doesn't like me. But say I pricked on one of these stations. And you can see the actual temperature and everything here. This is a way of looking at how the pressure has changed. So say I wanted the 3-day historical, and I'm going to look at 3 days historical as far as pressure goes there. Just for Charleston, West Virginia, I could have picked anywhere. I'm just picking one station to try it. And with that, I'm going to select my graph I want here. Once it gets done processing, and yes, Western region of the National Weather Service, that's a slow processor. But if it doesn't do it here in a second, we'll just stop with this one. But there you go. Here I'm going to select my graph I want. And what I want is sea level pressure. Notice at lower pressure earlier in the week, and it starts getting warmer and higher pressure here. This is a meteogram. You're going to be reading some of these in some of your labs. Pressure, y-axis, time, x-axis. I can plot a whole bunch of things on here at any time. All I need is a value for pressure and a time that value occurred. and then you can trace them. And the same thing would hold true if I went with temperature. And you can see the same exact thing. And you can put a couple of these on at the same time to give you an idea of what's interesting. Notice how the temperature dropped off last night really quickly, didn't it? Down to 54 degrees or 52 degrees for a while. But it's already cooled back, warmed back up to 73. So you can see the temperature changes in this kind of a plot. So take advantage of what you're seeing here with the meteograms and apply it to what you're going to have in those labs. So let me know if you have any questions.